Tonight, we welcome Professor Bertram Bitsch from the University College Cork in Ireland. Bertram finished his PhD in 2011 at the Institute for Astronomy and Astrophysics at the University of Tübingen. He then spent a little over 2 years as a postdoc at the Observatoire de la Côte d'Azur in Nice, France. From 2014, he became a senior research fellow at the Lund Observatory at Lund University in Sweden, and he lasted there until 2017 when he moved to the Max Planck Institute for Astronomy in Heidelberg in Germany, where he and his team studied how planets can form in different disk environments. In September 2023, he moved to University College Cork, where he continues his work on planet formation simulations. So let's give a big Mexican Swinton welcome to Professor Bertram Bitsch.
Thank you. I guess I can share my screen and start.
Share your screen, yeah. Yes, please.
Okay, fantastic. I assume you can see my screen?
We can.
Yes, perfect. Thank you very much for the invitation. So I will today talk a little bit about the formation of planets, also in the context of our own solar system. Okay. So in our own solar system, of course, we know we have the 4 terrestrial planets: Mercury, Venus, Earth, and Mars, and we have the bigger outer gas giants, Jupiter and Saturn, and Uranus and Neptune, our 2 ice giants. Of course, there's also some small asteroids in between Jupiter and Mars, and we will come back towards the end of the talk that these asteroids will actually hold clues to our understanding of the formation of the solar system. Just for perspective, these asteroids are very small. You see maybe here over here on the top, this very, very tiny white dot. This is Ceres, is actually the biggest asteroid in the asteroid belt, and you see how tiny it is compared to even the terrestrial planets. Now, very importantly, I will talk a lot about the distances from the planets to the sun or to a central star. So we normally use this unit, the astronomical unit, which is the distance between the sun and the Earth. So the Earth has a distance of 1 astronomical unit. Mercury and Venus, of course, closer in at 0.4 and 0.7 astronomical unit. Mars a little bit further away, around 1.5 astronomical unit. And then we see there's actually a bit of a gap towards the gas giants. First, the Jupiter with 5.2 astronomical units, Saturn around 10, and Uranus and Neptune sitting around 20 to 30 astronomical unit. And for those of you who are a fan of Pluto around 40 astronomical units, so even further away from our own sun. Just to put this into perspective, this is actually a very, very large difference of distances, because if you project this actually on a football pitch, you see that if the sun is essentially the point where you would start the game, you see that essentially even Jupiter would be within the central circle. And if we go all the way towards the goal, that's when we actually will have Pluto. And this can actually be a very, very long distance, especially if you actually play football and you have to do a penalty. This might you actually realize how large this distance is and how large our solar system actually is. Now, for our planets, we have, as I said, 3 different types of planets in our own solar system. We have the terrestrial planets, like the Earth, Venus with a similar mass. We have around the mass of 1 Earth mass, right? So we like to normalize things to things that we know. So we normalize our masses of the planets to Earth masses. So the Earth, of course, 1 Earth mass, and of course has 1 Earth radii. So that's the units we are gonna work with. In contrast, we have Jupiter, the biggest planet in our own solar system, around 318 Earth masses, and a radius of around 11 times the radius of the Earth. Now, Jupiter in itself, of course, has a very, very different composition compared to the Earth. It's actually it's a gas giant, so it mainly consists of hydrogen and helium, but of course also with traces of heavier elements like oxygen, carbon, and so on. In contrast, we have the ice giants like Neptune and Uranus in our own solar system. They're around 15 to 20-ish Earth masses, around 4 times the radius of the Earth. And we call them ice giants because they presumably contain a lot of ice. In this case, not only water ice, but also, for example, frozen out methane or CO2 that freezes out at even lower temperatures. So these planets are supposed to contain a lot of ice, but they are also covered in a small atmosphere of hydrogen and helium. Now, I want to introduce some techniques how we can find planets around other stars. One technique is the so-called Doppler technique. You know the Doppler effect, of course, from when an ambulance or the police car or the fire truck passes by, that you hear a change in the frequency. So if the source moves away from you, you get a lower pitch. So you hear differently, and if the source comes towards you, you hear a higher pitch of the ambulance or fire truck or whatever it is that comes toward you. So there's a difference in the frequency that you hear. Now, the same frequency, also the same change of frequency also applies to light that is traveling to us. So you could imagine a situation where you have a star and we observe the light from that star. But if that star is not fixed, but actually moving towards or in front of us, we will observe also a change in the frequency of the light that depends on the velocity of that star. So how fast is the star moving towards us or away from us? So we have here actually the equation. It's the only equation I'm going to show. No worries. So lambda is the wavelength of the light that we would observe. And the wavelength shift that we have is then equal to lambda 0. So the original wavelength of the light that we want to observe multiplied with 1 plus the velocity of the source divided by the speed of light. So it depends on the velocity of the source. Now we get a blue shift for a source that is moving towards us. So the velocity Vs is negative, which means the lambda will decrease relative to our lambda 0, so our original wavelength. And the redshift is we have actually a source moving away from us, so the velocity will be positive, which means the wavelengths will actually increase relative to the original wavelength. And we will see it rather, and the cartoon on the right is actually illustrating exactly that. So if something that comes towards you, you will see it blue, and if it moves away to you, it will look red. Now, we can actually apply this to find planets. Because if a planet is orbiting the star, both of these objects will not stay fixed. They will actually orbit around their common center of mass. And this means we can observe a shift in the frequency that we observe. So in the neutral scenario, so we have a reference spectra where, let's say, we would have a star without a planet. We would see the spectra as it exactly is. You see these small contributions here, these black lines in this colorful spectra. So this actually corresponds to so-called lines that we can observe, because each atom has specific lines, because the electrons in the atom can be excited to higher levels of energy, and when these a higher level of energies go down towards the ground state, they will emit photons within a specific frequency. And these are the specific lines. So these are individual and unique for each atom that we observe. So these lines are different, for example, for hydrogen compared to oxygen. Now we know in a neutral frame where these lines are supposed to be, because we can just test this in a laboratory on Earth. We can look where these frequencies are. This also relates back. It was actually done in the 19th century by Balmer, the so-called Balmer lines for hydrogen, where these effects were observed. Now, if we have this situation where we have a star, this continuous light source, and we have a planet around it, then as this planet moves towards us, the star will also move. And this means that if the star is moving away or towards us, this actually means that we will see a change in the frequency of the light, and also a shift of these transition lines that we observe. So if the star is moving towards us, we see a blue shift. So all these lines that we have in the reference spectra will move towards us. And that's why we call it the blue shift, because everything is shifted towards the blue part of the spectrum, of the visible spectrum in this case that we see. On the other hand, if the star is moving away from us, we will have the red shift. So all these transition lines that we have will be shifted to the redder part of the spectrum, as you see illustrated in this cartoon. And we can use this now to observe exoplanets. So again, as I said, we have a system here in this case of a star and an exoplanet, and they will both orbit around a common center of mass. And this movement of the star around the center of mass will change how we see the star. So as the star moves closer to us, we will have a blue shift, and as the star moves away of us, we have a red shift of our spectrum. Now we see here in the bottom, that's the velocity of the star towards the Earth in meters per second. As the star is moving closer to us, we see that there's an increase in this velocity towards us, and as the star is moving away from us, we have the decrease in this velocity. Now, this change in the velocity is, of course, proportional to the velocity of the star, which in turn depends on the mass ratio between the planet and the star. So you can easily imagine if you have a planet that is very, very massive, it will influence the star more than a very, very tiny planet. So we will have larger shifts in this velocity for larger planets, and we will have smaller shifts for smaller planets. And this means directly that it is much, much more difficult to find smaller planets, because this change in the velocity will become not meters, as it is here shown in the diagram, but will go towards centimeters. And that becomes very, very hard and very, very difficult to observe with a telescope. Another detection method to detect action planets is so-called transit method. So the idea is we have a star, we have a planet that orbits around it, and we can observe the brightness of the star and planet system. So in the beginning, we will have our planet not in front of the star. So we have the stars at the maximum apparent brightness. But then as the planet starts to move in front of the star, the brightness starts to dim. And once the planet is fully in front of the star, we have reached the minimum starlight for our telescope. As we move out, the star begins to brighten again. And of course, as the planet moves away from the star, we have again the maximum apparent brightness. Now, this dip in the brightness that we observe is proportional to the size of the planet compared to the size of the star. Right, so you can easily imagine if you have a super tiny planet, you will not see too much of an effect. But if you have a large planet, you will see a large effect. We can even go to very extreme cases. If the planet becomes very similar, let's say in the size of the star, we will see a very, very deep drop in this apparent brightness. So with this method, we can determine the radius of planets. Now, in order to determine if it's really a planet, we actually need to observe multiple transits of the same planet, because in this case we know that we have a periodicity of the planet orbiting the star, and not some other effects. For example, you know probably about sunspots, solar spots that also change the brightness of the star, and we have to be sure that what we see is actually related to the planet. So it needs to be observed on a regular basis. We see this directly here in this diagram. So we have the time evolution in days and the brightness on the y-axis of this diagram. And you see that the time difference between the first and the second transit is, of course, the same as between the second and the third transit. So we have the periodicity of the planet going around the star. And this gives us an indication that there is actually a planet going around. Now, there's another interesting method to detect planets. It's the so-called direct imaging method. The idea here is we take a very big infrared telescope, and we directly look for the infrared radiation of the star. And this is one of the most famous systems that we found with this method. Is the Eire 799 system. It has 4 planets. So we have the planet B, C, D, and E. I know, very creative with namings, but this is the easiest way to keep track of them. So we have 4 planets. In the middle, there's the star. You see, you don't see the star actually, because the idea here is that you, of course, put something in front of the telescope to get rid of the light of the star, so you can actually see the planets, because the light of the star will, of course, outshine the light the emissions that we see from the planets. So in this case, we have 4 giant planets around the system. You see here on the bottom, you see also the size bar. So this distance corresponds to 20 astronomical units. And if you would see and do this all the way to planet B, you would actually see that planet B is around 70 astronomical units away from the central star. So much, much, much further away than the outermost planet in our own solar system. So this system is much, much larger than our own solar system. In addition, these 4 planets that we have here, they're actually several times the mass of Jupiter. So we have very, very large gas giants within this system. Now we can combine all these observations into a diagram like this. So we have here on the x-axis the single major axis in astronomical units. And on the y-axis, we have the planetary mass that we can determine, for example, via the Doppler effect. Now, in this diagram, you have here the Earth, you have Jupiter, and we have Neptune, and their corresponding orbital distances and their corresponding planetary masses. All these other dots that you see here originate from exoplanets that we have detected. The different color codings here correspond to different detection techniques that we can use. So the purple guys that you see here, this corresponds to planets that we have detected via the transiting method. So the planet moving in front of the star. The green dots correspond to the radial velocity, so the Doppler effect that we just discussed. Now these reddish planets are far away beyond 10 astronomical units, and you see several times the mass of Jupiter. These are the planets we found with direct imaging, so the last method that I introduced to you. There's a few other colors in this diagram because we have some other methods that we can use to detect planets. I will not go too much into the detail, but I'm happy to discuss this later on. Now, what you see directly in this diagram, there seem to be some groups of different types of planets. Right? So you see, for example, a group that is very similar to our own Jupiter in terms of orbital distance and in terms of mass. So these planets we normally refer to as cold Jupiter planets. Cold because they're far away from the star and have a very low temperature. In contrast, you see this group of planets, mainly purple in color, so mainly found by the transit method. These planets, they have similar mass to Jupiter, so they are Jupiter-type planets, but they're very close to the star. You see down here, they're actually orbiting within 0.1 astronomical unit, so even closer than Mercury. And these planets are then the so-called hot Jupiters, because these planets orbit very close to the star, and they receive a lot of irradiation from their host star, and are heated up quite massively. In addition, we have this third group of planets down here. So these are planets with a few times the mass of the Earth, but they also orbit very close to their central stars. And these planets are the so-called hot super-Earth planets, which with masses of several times the mass of the Earth. The idea here is we don't really fully know what they are made of. Are they made rocky? Are they rocky planets with an envelope? Or maybe are they the ice-rich worlds that moved from the outer solar system to the inner system? We don't know. This is something we want to try to investigate. Now, of course, one has to say there's a lot of bias within this plot, right? Because of the first bias is I think quite easy to see, is that if you go to planets that are small and far away from the star, they become much harder to detect. The reason for that is if the planets are very small and very far away, you will basically see nothing within the transit method. We will see no real dip in our brightness curve. And for the radial velocity, if your planet is too small, you will also not generate a large radial velocity component towards our central star. So these planets are very hard to detect. Additionally to that, there's of course a bias in this plot, right? Just because of the detection efficiency. Because it's, as I said, it's much easier to detect the big planets that are very close to the star compared to the small planets that are further away. So in order to understand the exoplanet population, we actually have to calculate the occurrence rates for our different exoplanet surveys because of the different biases of our detection techniques, right? So you see directly, for example, the transit method, the purple planets that we have here in this diagram, they're normally limited to distances to 0.3, 0.4 astronomical units. So with these detection techniques, of course, we can make no prediction to planets around 1 to 5 astronomical units. But this we have to rely on different detection methods. And one of the questions that I try to understand in my study is to understand how these different groups of planets could form. Now, the systems that we observe, they are, of course, not only single systems. You can actually have planetary systems that have multiple planets. So you see here a transiting planetary system. So this is again the same a transiting curve as I showed you before. So you have the relative brightness, and then you have the dip of the brightness, but actually we have several dips and plateaus within this observation. And this is actually related to the fact that we have 3 planets transiting simultaneously in front of the star. So we have three planets moving in front, and they all, of course, reduce the brightness of the star. You see this actually indicated here in the bottom of the panel. So the black circle would correspond to the surface area of the star, and then we have these planets here, C, E, and F in this case of this system, and they all move in front of the star. So you see here you have this drop in the brightness curve when the planets F and C actually move in front of the star. Then the third planet enters here. We have the deepest position in our brightness. Then the 2 planets F and C are actually moving away from the star again, so our brightness increases again. And once also planet E has left the front of the star, you go back to our baseline, our relative brightness. Now the system here is the Trappist-1 planetary system. It's a very, very interesting planetary system because it contains 7 planets that orbit a very small mass star. So the star is less than 10% the mass of our own star. So it's a very small star, which means that it emits even less light. Now, the very, very interesting part here is that these 7 planets actually form a so-called resonance chain. So this means, for example, when the inner planet goes around the central star, let's say twice, the next star will only go around once. So we have a resonance. It's the same resonance as you have, for example, if you play the piano or any other musical instrument, you have the resonance. It's exactly that. What we have here. So we have a 7-planet system in a resonant configuration, which of course gives us indication for the formation of these planets. Now, for a comparison, so the Trappist-1 planetary system has these 7 planets, and they're very, very similar to the terrestrial planets that we have in our own solar system. So you see here the planetary radius and the planetary masses of these guys are around one-ish Earth radii, one Earth masses for B and C. D a little bit smaller, but F and G already within the same scheme. Now, additionally, these planets, of course, orbit much closer to the central star. So you see the innermost planet in the Trappist system orbits the star at around 0.01 astronomical units. So much closer than Mercury, which sits at roughly 0.4 astronomical units. Even the outermost planet H sits only at 0.06 astronomical units. So it orbits the central star within 20 days. So so the system is very compact compared to the solar system. So you can actually look at this in an illustration here. So you see here on the bottom, the inner solar system, and these small green lines, this would correspond to the distances that this planetary system would actually have if it would be within our own solar system. So super close to the central star. Now in this plot, we have also these 3 different colors indicated in the bottom, and they actually correspond to the region where we could have liquid water, right? We know we have liquid water on Earth. We also know that there was liquid water on Mars in the past. So this corresponds to this green region. Now, as I said, this Trappist-1 system orbits a much smaller star that is much less luminous and therefore emits less energy. So everything is much colder within the system. And so actually these planets E, F, and G, they would orbit in the same zone as the Earth, where we can find liquid water on the surface of these planets. So this is why these planets are very crucial interest for our understanding of planet formation, and maybe to understand if there's life on other planetary systems. Now, for this planetary system, we actually have an amazing advantage because we can observe the system not only with the transit method, but also with the radial velocity method. And this gives us suddenly new information about the planet, right? With the radial velocity method, we could determine the mass of the planet. And with the transit method, we could determine the size of the planet. But if we have the mass of the planet and the size of the planet, we can actually calculate the density of the planet. And this allows us to make a comparison to our own solar system. So we have here the density of the planet in units of the Earth's density. So we normalize it to the density of the Earth. And on the x-axis, we have the illumination of the planet. So essentially, what is the illumination that you receive from the star? And you see the Earth, of course, it's at 1 Earth illumination. So this actually corresponds to this green area in this region. And now, if we compare the planets of the Trappist systems, these are the brownish circle, we see that they're actually very, very similar to the solar system in terms of their densities and in terms of their illumination. So essentially, one could claim that the Trappist system is a squeezed down version with a few more planets compared to our own terrestrial planetary system, which makes the system very, very interesting to study, because we have to understand how these systems can form. Now, there's other planetary systems that we find, and these planetary systems have very interesting properties. So what you see here in this diagram is different planetary systems. They have all these weird numbers, and you have here a Sol, which is the solar system. What you see here, these lines correspond to their distances in astronomical units. You see for the solar system, we have the Earth, of course, sitting at 1 astronomical unit. Now, the exoplanetary systems that we found, they're much, much closer towards their own central star. So they're mostly within the orbit of Mercury in our own solar system. But now there's a very interesting property of these planetary systems, because if you look at each planetary system individually, like for example, if you look at this system down here, it seems that all these planets have the same size and that they are all also spaced very equally. And this actually indicates that these planets would form something like peas in a pod, right? So if you grow peas, they come in this pot, and they're all like similar-ish in size, they're similarly spaced, and this is a very nice comparison to the properties of these exoplanets. So they're like peas in a pod, right? I mean, of course, you have differences in the sizes of the planets between different systems. It's the same as the peas. If they grow bigger, you have, of course, bigger peas. But within each system, this seems to be relatively true. And this means these systems, the planets in these systems, have similar sizes and also similar masses, which is something that we have to understand from a formation perspective. Now, how do these planets actually form? Well, we normally start with the formation of a star. So we have a gigantic molecular cloud consisting mainly of hydrogen and helium. You see these clouds are very gigantic, around 20,000 astronomical units. They collapse, they will start to form a star, and you will form a so-called protoplanetary disk around it. This is mostly caused by the fact that this cloud has a little bit of a rotation, and then as it starts to contract towards the center, it will flatten out and form a disk rotating around it. Now, within this protoplanetary disk that consists mainly of gas, but also of dust, we can start to form the planets. We can observe these protoplanetary disks. So this is a picture from the Hubble Space Telescope of the Orion Nebula. And you see these weird-looking objects, these disks around young, newly formed stars. Now, within these disks, we can form planets. But in our days, we actually have much, much better instruments to look at these disks. So this is an image of a protoplanetary disk surrounding a young star. This is taken with the ALMA telescope, so the Atacama Large Millimeter Array in Chile. And you see it was published around 10 years ago. So it's very, very recent observation. What you see here in this protoplanetary disk is the thermal dust emission of millimeter-sized grains. So you have millimeter-sized particles that emit radiation, and we see here the millimeter-sized, the contribution of these grains. So there's a few things that you notice here. So first, if you look at the size bar again, so this corresponds to 14 astronomical units, you again see that this protoplanetary disk is very large and much larger than our own solar system. Additionally, you see that there's bright rings and darker gaps. And this indicates to us that these bright rings will contain more dust, so we get a larger emission compared to the small gaps where we have less particles and we have less emission. So we have not a continuous distribution of this dust, but we have a ring-like structure of these protoplanetary disks. So now how do we put this together? So what we have here is another image from a protoplanetary disk, but it's a different instrument. It's with the very large telescope in Chile that actually observes micrometer-sized dust grains. So the much smaller dust grains. Again, in this protoplanetary disk, we see these bright rings and darker gaps. But now we can observe the same disks at the millimeter wavelengths, so we can see the millimeter-sized particles. So this is the same disk at the same scale. Okay, so what this indicates to us is that the grains are of course not distributed uniformly in the disk, but they are more concentrated towards the center of the system. And we also see that maybe the grain growth, so the growth from these micrometer-sized dust grains or to millimeter-sized dust grains would happen preferentially in the inner regions of the protoplanetary disk. So how do we put this together? Well, we have our grains, our dust grains in the protoplanetary disk, and we can observe the exoplanets as the end product of planet formation. This means we have to go over 13 orders of magnitude in size. So we go from the small micrometer-sized dust grains all the way to the giant planets. And this, of course, means we have to model this growth of the planets. And this is what I would like to talk to you a little bit about. So how do we model the growth of these planets? Well, we start with the protoplanetary disk with the millimeter-sized dust grain. So we have here the size bar where we want to go from the micrometer-sized dust grains that the disks contain all the way to the planets. So the first growth step that we have to take is we have to grow from dust to millimeter-centimeter-sized planets. And this can happen through coagulation. So essentially grains collide and we can grow, or also to condensation at so-called ice lines. So for example, you can have a dust grain, and water can condense out of it, and your grain can grow. The next step is how we can transform these pebbles into planetesimals. So if you have a large cloud of these millimeter-sized pebbles, it can collapse under their own gravity and form a planetesimal. A planetesimal, think essentially about something like an asteroid, like kilometerish in size. Then these planetesimals, they can collide and continue to grow and form so-called protoplanets in the disk, similar to like Mars or moon size. Additionally, these planets could grow by accreting the leftover of these millimeter-sized dust. Once our planets have reached a mass of a few Earth masses, you can start to accrete gas onto these planets during the protoplanetary disk gas phase. So we know we can observe the initial conditions of planets, so the protoplanetary disks for micrometer and millimeter size, and we can observe at the very end the final planets around other stars. But in between, we have no observations in other systems. In the solar system, of course, we can observe the asteroid belt, but we cannot do so in exoplanetary system. So this means directly that to understand planet formation, we have to understand a great deal of physics, how we can grow from micrometer all the way to objects that are tens of thousands of kilometers in size. And of course, it also means we cannot observe, model every dust grain individually, because we cannot, there's no way we can actually model this. So we have to run different simulations with different numerical approximations to model the growth process from the micrometer-sized dust grains all the way to the giant planets. And this is essentially where my work comes in. So the first thing is what I would like to do is talk to you a little bit about the formation of these super Earths, as you see. So this is, of course, an illustration of what a super Earth would look like. Okay, so what I'm going to do, I'm going to show you a movie from one of our simulations. So what you will see here is a time evolution over a few million years, where we start with small planets, moon mass planets that will continue to grow and move through the protoplanetary disk. So let's start the movie. I hope you can see the movie. So you see the planets start to grow by accreting these millimeter-sized pebbles. They start to also move through the disks through gravitational interactions. And they move slowly towards the inner regions of the protoplanetary disk, where they first form a resonance chain, but then we have some collisions between the planets as the system moves along. So in the end, we form a system with a few planets in the inner region of it. Now we can look at it in a graph that will give us a little bit more information than the moon. So we have here on top we have the single major axis as a function of time. So over the first 50 million years of evolution. In the bottom, we have the planetary mass of the objects in our simulation, also as a function of time. So what happens as we start off our simulation, you see a very smooth growth of the planets initially, and this corresponds to the accretion of other planetesimals of pebbles in this protoplanetary disk. Then at some point they stop growing because you run out of pebbles, but then you have these small step functions in their mass function. This means we actually have two protoplanets that collide and form a bigger object. Towards the end of the lifetime of the protoplanetary gas disk, it lasts a few million years, the planets will actually undergo again a phase of instabilities where the chain of this resonant configuration that we have can be broken. And the planets will acquire, as you see here in the bottom right, some degrees of mutual inclination. And this actually is very important for our understanding of the observation, right? So you can imagine we have a star, let's say we have 5 planets in it, and we have a telescope that looks at it, and if these planets are all within the same plane, we can maybe see all 5 planets are transiting at the same time. However, if the planets have a small levels of mutual inclinations, we might only see one planet transiting because the other planets are out of orbit. This actually applies also to the solar system. So the solar system, the planets actually have a little bit of mutual inclination. So if you would be an alien observer and you would try to observe the solar system via the transit method, you could maximum see only 3 planets transiting at the same time, no matter how you would put your telescope. So even a small level of inclination will change our observational property. Now we can try to understand how our simulations actually do in comparison to the observations. So for this, we have to actually run many hundreds of simulations and then analyze the results of these simulations. So what we have in this plot, so this is a so-called cumulative distribution. This means if you basically take the value of each of these pillars and would add them all together, you would arrive at 1, where 1 means we have accounted for everything. The gray line here corresponds to the observations of exoplanets via the transiting method. The green line here would correspond to our best fit of our simulations. So we do actually quite well to reproduce our observations. Now, the interesting part here is the color coding within this diagram. So because the first pillar that you have here means we have 1 planet per system that is detected by transit. But in our simulations, we of course know how many planets we have in each system that we have. So most of the planets where we would have only 1 planet detected by transit, most of these systems would actually contain 2 or even more planets. The reason for that is again this mutual inclination between the planets that allow us to only see 1 of those planets transiting most of the time. And the same story is true if you have a look at systems where we have 2 transiting planets, then our simulations would actually predict that the majority of these systems should actually have 3 or more planets, so that there are hidden planets within these transit observations. And this is something that we're actually trying to observe, because if you have a system where we know we have just 1 or 2 transiting planets, we can observe the same system with the radial velocity method, and then we can actually see planets that are also not transiting. So we can actually check if our model is true, and if it works out, great. If not, we have to go back to the drawing board, and it will help us to understand the planet. Now, I would like to go back a little bit to our own solar system. So again, we have our 4 giant planets, and we have our terrestrial planets. So if you want to model the growth of the solar system, there's a few things we have to make. First, we can start with some assumptions because we don't know how the solar system was formed. So we can start with some assumption, and we want to check if that assumption is true. So we could make the assumption that the giant planets are already formed, and that the inner regions of the disk, so the terrestrial planet zone where we are, what filled with these small planetesimals, and that our gas disk lives a few million years. There's a few things we do not know. For example, what was the exact position and eccentricity of the giant planets at the time of the solar system formation? We don't know how much mass we had in the planetesimals in the inner regions of the system. We also don't know when exactly the disk dissipated. But of course, we have some constraints, right? So if we do a simulation, we want to model the solar system, of course, these simulations need to match the planetary masses and orbits, right? We need, if we want to understand the formation of the solar system, we of course have to reproduce the solar system. Additionally, another constraint is the structure and distribution of the asteroid belt, how it is, what is their composition. And we have to match the water content of the terrestrial planets, right? We want on Earth that is water rich, that has enough water. And even more complicated, we have to match the isotopic composition of the Earth. But I will not go into this. So let's just focus on masses and water, something much, much easier to understand. So let's start with a simulation, okay? So we have a simulation where we say we have a Jupiter, and then we have a disk of these small planetesimals interior to Jupiter, and we say Jupiter and Saturn form at their current orbits and don't move through the disk. So this is the movie of the simulations. We have the same major axis on the disk. This big black guy here is Jupiter, and then we have here our initial planetesimals that can collide and form larger objects. So the size of the dot would mean a larger object. The color coding in itself corresponds to the water content of these planets. So blue means water rich and red means water poor. At 10 million years, the disk goes away, so we do stamping effects, and the whole system becomes very unstable. And we see the collisions between the planets. The planets start to grow. At the moment, it looks like we will have no way of making terrestrial planets because we have way too many planets sitting around here. But as the simulation goes on, we are now at like around 80 million years. If you go towards the end of the simulation, at around, as you will see, over 100 million years, 200 million years, you will actually arrive at the final planetary system. Let me stop the movie here. So we have here a planetary system compared to the terrestrial planetary system that we have in our own solar system. We see we have a few too many planets, actually. Additionally, the planet that are supposed to be correspond to Mars, you see is actually the same size as the Earth and Venus. This directly indicates you, well, something did not work out in this simulation if you want to reproduce the solar system. Now we can actually change our initial condition. So it's the same set of simulation again, but now we say we have a small eccentricity attached to Jupiter. And this small eccentricity means that Jupiter will move a little bit closer to the inner regions of the disk, and therefore influence the structure of the inner planets as they grow and as they collide. Now, again, at 10 million years, the gas will go away. Our systems will become very unstable. If you go towards the end of the simulation, around here, around 200 million years, we actually produce Venus and Earth quite well. But if you look here at Mars, seems to have the correct mass. But you see Mars here is super blue. And this super blue indicates that Mars has way too much water. So again, our simulation failed. So we can summarize this. So if Jupiter and Saturn were in a resonance configuration, circular orbits, we overshoot the mass of Mars because we don't have a mega Mars, so we just have a small Mars. So the simulations fails because our planets become too massive. On the other hand, if we have Jupiter and Saturn in a bit of an eccentric orbit, we change the outcome of our simulation. So we see we can actually match the mass of Mars quite well. But our Earth would be too dry, so we don't have enough water. So again, our simulations fail. So how can we proceed from that? So there's actually, we have to go back to our initial assumption. So our initial assumption was that the inner disk, interior of Jupiter, was all filled with planetesimals. Well, let's change that assumption. So one idea that was put forward as well, what if you only have a tiny ring of these planetesimals in the inner regions of the disk that would then form the terrestrial planets? Then we actually get a much nicer match to the observations of the terrestrial. So in this diagram here, you see the planetary mass in Earth masses and the distance in astronomical units. So the black dots correspond to our terrestrial planets. So Mercury, Venus, Earth, and Mars. And the white dots would correspond to the results of the simulations. And you see this actually matches quite well. The question that you can now ask is, well, but why should the ring be so small if you have planetesimals initially everywhere? So one idea that was put forward is, what if actually Jupiter was much closer at some point in the past? So Jupiter was much closer. This means, well, you would not have that large disk of planetesimals. But of course, if you have Jupiter and you would put it, let's say, at 1.5 astronomical units, you have to move it out again, because I mean, obviously Jupiter is at 5.2 astronomical units. So you have to move Jupiter out again. There's actually a process that allows you to do exactly that. So in a classic protoplanetary disk, Jupiter would open a gap, and then it would be locked inside this gap and move inward due to the exchange of angular momentum between the gas disk and the planet. But now, if you have two planets, let's say Jupiter and a smaller version of Jupiter, let's say Saturn, in a common gap, then they can reverse the direction of migration. And this is caused by the fact that the inner disk will cause a torque on the inner planet that will start to move it outwards, while the outer disk will exert a torque onto the outer planet to push it in, but that is proportional to the masses. So if you have a mass ratio for Jupiter and Saturn that would correspond to this of around 1/3, they can both move out again. And this can actually give an application to the solar system. It's the so-called grand tag scenario, where the tag actually comes from sailing, where you try to sail against the wind. And this is the outcome of these simulations. So you have 6 different panels that correspond to different time evolution. So you have here at 0 million years, at the initial condition, 70,000 years, 100,000, 300, 500,000, and then at the end at 150 million. So initially we have our four planets. We have our inner terrestrial region filled with dry planetesimals. Jupiter moves in, and then it pushes everything towards the region of the Earth. So we squeeze our inner ring of planetesimals. Saturn comes in, and Jupiter and Saturn both move outwards again. In the process of this inward and outward migration, we actually implant dry and also wet planetesimals into the asteroid belt, and this is exactly what we observe. So this scenario could explain why Mars is small, why Earth has the correct water, and why we will have the composition in the asteroid belt. As you see here in this plot, just to emphasize this again, this is the final masses of the simulations versus the masses of the terrestrial planets. You see we can actually match the mass of Mars very, very well. Now, to emphasize this again, so the idea is we have Jupiter growing, then it starts to move inwards in time. Saturn comes, they catch in resonance, and then they move outwards to their current position. However, at the end of this scenario, they are still in a resonant configuration. And this is, of course, at odds with the solar system today, because Jupiter and Saturn are not in a resonant configuration. So we can solve the problem of small mass, but we pay the price that now Jupiter and Saturn are in a resonance. But of course, there's also an idea how we could actually get rid of this. So the idea here is that we have Jupiter, Saturn, Uranus, and Neptune in a resonant configuration on circular orbits, but we have an outer disk of planetesimals. And these outer disk of planetesimals, if we have enough mass there, these will act a gravitational force onto the planets, and this will cause an instability of the planet. So we also have a movie for this. So we start our simulations with Jupiter. Then we have Jupiter in red, Saturn in yellowish orange. And then we have Neptune in blue, and then we have Uranus outside. You see in most of these simulations, actually, as you will see later on, Uranus and Neptune will actually shift their orbits. We have the Kuiper belt, 30 is Earth masses, and the simulation goes around. You see some small tugging of these planetary orbits, and then we have suddenly an instability that changes, that breaks the resonance of these planets, and we are left with our four planets at the end of the simulation. What also happened here is that Uranus and Neptune actually changed their position. It's actually very common in these type of simulations that we have a flip between the ice giants just because of the exchange of angular momentum. It's just a different set of simulations, but essentially you would see exactly the same thing will happen. That we have an instability after a few hundred million years of the solar system evolution. And with this instability, we break the resonances of Jupiter and then also Saturn within our simulations, and then give us an idea how the solar system could have formed. Now, of course, the question is, when did that instability actually happen? And this is actually, we can actually constrain this by the crater record on the moon and on Mars. So you see here a picture of the moon. So this is the near side. So this is the near side of the moon that we can see from Earth. But on the other side of this picture, we actually have the far side of the moon. So this is the side of the moon we actually never see from Earth. And we actually have seen this the first time with the Apollo missions. And you see here, there's a lot of craters on the moon. And the moment we can actually investigate these craters and look at the rocks of these craters, date the rocks, how old they are, we can actually constrain the timing of the instability. So it's actually very crucial to have good samples of moon rocks to actually understand when that instability has happened. We can put this all in a diagram together. So we have here on the y-axis the semi-major axis, and then we have the time evolution of our system. So first, we have accretion of our planetary cores by pebbles and planetesimals. Then we can start to, Jupiter can start to accrete gas. It migrates inwards. Then Saturn follows. He captures Jupiter and Saturn in resonance. Both of the planets move outwards. They remain on this quasi-circular resonant compact orbits for around 100 to 200 million years. And then we have this instability where we put the planets in our current orbits right now. Additionally, this instability will cause the impact craters onto our moon. Now, if you paid very, very close attention, you actually see that now in this diagram, I say the instability is around 100 to 200 million years after the formation of the solar system. But in the movie, the instability happened around 700 to 800 million years. So there's a difference here. And this is because we had to revise the time of the instability due to our new interpretation of the rocks that we have from the moon, from the Apollo missions. So I think it's very crucial to go back onto the moon, to get samples back to our laboratory in order to understand when this instability really happened. And this directly brings me to the summary of my talk. So we have different detection methods for planets: a transit method, a radial velocity or Doppler method, direct imaging, and other methods. So we can find a lot of planets around different stars. These planets form in so-called protoplanetary disks. The dust can grow all the way to planets. This formation process is very complicated as we go over many, many orders of magnitude in size, but we can build models to explain the systems, of course, governed by the constraints that we have. For the solar system, of course, we have a lot more constraints than for the exoplanetary systems, because for the exoplanet systems, for example, we don't really know what is the water content on these planets, but we know this, of course, very well for Earth. So we have more constraints from the solar system, but we still need to put all these pieces together to really understand the formation of the solar system. With this, I thank you for your attention. I'm happy for any questions.
Well, thank you for a very comprehensive introduction to planetary formation. Could I ask you to stop sharing your screen?
Of course.
And then we can see all the guilty parties. As usual, ladies and gentlemen, if you have a question and you're online, will you put a digital hand up? If you're in the room, could I ask somebody to just turn on one of the mics to the rear of the room? Try and attract my attention, and we'll get you into the conversation either way. So we're looking around for questions, and I'm not seeing anybody. Oh, Tony Morris in the room.
Hi, thank you for that. That was really comprehensive. There's a lot to take in. When you were talking about the interplanetary disks, in the models, do you vary the density of the disks? And how much effect does that have on the timescales for planetary formation?
Yes, excellent question. So the density of these disks plays a huge role. So normally what it's doing is there's actually a time evolution of these disks attached to it. So we start normally with a very massive disk, and then over time the material falls onto the star. So the disk density decreases in time. This has the effect that it will change how the planets can actually move through the disk and how they can grow through the disk. You can maybe think a little bit about this, that like if you have a very massive disk, you have a lot of material, so the growth will be much faster than if you have a disk in the later stages where you don't have that much material left. So that will change the growth rate of the protoplanetary disk. This is something that we vary in the simulations, but we are normally also motivated by the constraints that we have from the observations of these protoplanetary disks. So we will choose in these simulations as initial conditions for the disk masses that correspond actually to what we have from the observational constraints.
Okay, thank you. Mick Nichols online.
Yeah, sorry, I was just looking for my buttons. I watched an episode of How the Universe Works this morning, and it was quite an interesting topic because it said that to get the elements, what we've got in our solar system, in the right levels, we need two supernova explosions, a type 1 and a type 2. And it also stated that we had the odd solar system out. No other solar systems look like us. And that got me thinking, and I thought, well, if that's the case, then surely it puts a nail in the coffin again of life around other planets. Because if the Earth's the odd one out, then life has to be the odd one out. And the chance of two supernova explosions, a type 1 and a type 2, in another solar system must be trillions to one again, surely.
Yes. So there's, I think, a few aspects to this. So the first aspect is maybe related to the fact how unique is the solar system, or how unique is the Earth. So I think we cannot really put a nail in the coffin to that, because it is very, very difficult to detect Earth-sized planets at a distance of 1 astronomical unit around solar type stars. So there's maximum a handful of these planets that we have detected so far. And this is not because these planets do not exist, but this is because our detection capabilities are not good enough yet. So we are building new machineries that will hopefully shed light on this in the next couple of years, so we can actually get a much better statistic to this. Because with the current observations that we have, essentially, if you would observe the solar system, the only thing that you would see at the moment is Jupiter, which, you know, is a good indication, of course, but it doesn't tell the full story. Additionally to that, in order for life to develop, it is not guaranteed that you actually need a Jupiter-sized planet, right? Because, I mean, you're sitting on an Earth-sized planet. So you do not necessarily need a system that has a gas giant in it to form life. To go to your question about the two supernovae explosions, so the idea here is that as the stars form and as they explode, they generate different elements, and they also generate different isotopic compositions of these elements, right? So you know maybe that, for example, for uranium, you have the uranium-235 and 238 that, like you know, is essentially it's the same element, but they have a different isotopic number essentially. And in order to get the direct data that we have on our Earth for the isotope ratios, you need to have these two events happening to match directly the isotopic composition of the Earth. In my view, this is not necessarily an indication that we need life to make life, right? So I think what matters in order to have life is that we have liquid water on the surface. But this is essentially independent of the exact isotopic ratio, I don't know, for uranium, silicate, magnesium, molybdenum, or whatever element that we actually have on the Earth. For the Earth, we have the advantage that we can get very detailed understanding of the isotopic composition of the Earth, also from meteorites that come onto the Earth. So we can construct a very, very detailed model for the solar system. And this is something we can never hope to achieve in the next couple of years for exoplanet systems, because we just don't have the data. So I would not really see this as like, you know, a showstopper towards, you know, life around other systems, or saying that the solar system is like the complete oddball, because I think we don't really have enough data to do this at the moment.
Thank you.
In the room, Gary, please. Right. Oh, right first then. Yeah.
Thanks for the talk, Bert. I was wondering on the model where Neptune moves out of the solar system. It always has puzzled me, how does it get past Uranus? Because they're both in the same plane. At some stage they must have been very, very close. So without them sort of changing inclination drastically, I can't see how they can get past each other without some really big interaction. And would that explain Uranus's axial tilt, maybe?
Right. So I mean, they have a little bit of mutual inclination between Uranus and Neptune, but you have to also think about it that Uranus and Neptune are very, very far away. So even if you have a tiny bit of inclination, which actually amounts to a large distance. And additionally to that, the planets are not always in the same on the same side, right? You know, if my head is the sun now, and you do not need to have both planets here. You can also have one here and here, right? So there's certainly a way for this to make it happen. Regarding the actual tilt of Uranus, my understanding is from these type of simulations, you cannot get the actual tilt of Uranus. So one of the leading models at the moment is that Uranus actually had an impact of like an Earth-size planet that would actually change the rotation of the planet to the tilt that we are actually observing. Because the moment you have a collision, you can also change the rotational axis of the planet. It's also one of the ideas why the Earth has this you know, 23 degrees a change of the actual tilt. That it might be related to the impact it generated the moon.
Yeah.
Gary, please.
Yes, great talk. Thank you very much. Really enjoyed it. Just a little bit of kind of fun about what you've been doing is that you've modeled things from the past up to the present. Have you ever really had to go out like forward modelling and see if there's enough random material in the solar system to have any major impact, or are we just really at a stable state now?
You mean how the solar system would evolve towards the future?
Mm-hmm.
Yes. So in principle, there's not more new material essentially left. I mean, we have a few asteroids in the asteroid belt. We have, of course, our terrestrial planets, but essentially the solar system is stable since now a few billion years. If we would do the calculation into the future, we can actually find that, for example, Mercury could be expelled from the solar system within the next a billion years. There's a 10 to 20% chance that this might happen, just from the you know, uncertainties that we have for the calculation of the planetary orbits over these long time scales. So it might be that we will lose Mercury in the next billion years, but it will not affect us.
Okay, Gary.
Yeah, I won't be around for that.
Okay. Peter Lloyd, online.
Yes, thank you for that talking. I've got two questions, actually, if I'm allowed to ask both of them. You mentioned just a little bit earlier about isotopic compositions. And as I understand it, different meteorites have given different results for the ratio between the two oxygen isotopes. And this rather implied that the original disk had different compositions of the ratios of the oxygen isotopes in different parts of the disk. And I wondered whether you have any possible explanation about how that could come about.
Yes, so this actually relates back to the previous question about the type 1 and the type 2 supernova, right? Because they would generate oxygen with different isotopic compositions. And then within the solar system, the question is whether the material from these supernova explosions, where it would land, if it would land in the inner regions of the disk or in the outer regions of the disk. So there's the idea that as Jupiter formed, essentially it stops the material from the outer regions of the disk to reach the inner regions of the disk. Okay, we have then a baseline, let's say oxygen isotopic composition. Then we have Jupiter, and then if you have the infall from new material, it will hit the outer regions of the disk, and the material, the planetesimals that will form in the outer regions of the disk, will then have a different oxygen isotopical composition compared to the inner regions of the disk. And then as the system evolves, of course, we have a mixing of these asteroids again, so that we can actually find the meteorites of both of them in the on Earth as they impact the Earth.
Oh, sorry, sorry, I hadn't realized that the idea is that these two supernova explosions occurred after the disk had formed,
Yes.
rather than earlier to seed the cloud from which they formed.
Yes, so the idea is that they happen during the formation, so we can actually influx new and different material into different disk regions.
And that could happen without disturbing the disk so badly as to...
Yes.
Yeah.
So, I mean, infall is very common. We observe this in a lot of protoplanetary disks, and the disks happily still rotate as some material is falling onto them. So there's no problem regarding that.
I understand now. If I may ask my second question, which is quite different. I'm not going to pretend I understood your explanation about why resonance between Jupiter and Saturn cause it to move outwards, but I have heard that before. My question is simple enough. Is where does the energy come from? It needs energy to move those planets outwards. Where does it come from?
Yes. So so essentially there's an exchange between the planets and the protoplanetary disk that they are still embedded in. So the inner disk is rotating faster than the planet. So the inner disk, as it rotates, you can imagine that there's a, let's say, that there's a force from the inner disk that will basically pull the planet along, so it will accelerate the planet, right? And at the same time, the outer disk is rotating slower than the planet, so it will pull the planet back, so it will decelerate the planet. Now, if you do a calculation for a single planet, this means the planet, the net force onto the planet will be such that the planet would move inwards. But now, at the moment, you have two planets that are in a resonant configuration. This means the inner disk will act onto the inner planet, while the outer disk will act onto the outer planet. But this force is proportional to the mass of the planet. And since the inner planet, aka Jupiter, is bigger than Saturn, the net movement is suddenly outwards. Because essentially the force, as we know, the gravitational force is a function of distance, right? So the further away you are, the less it actually works. And this is exactly what's happening. So your inner planet is much further away from the outer disk than from the inner disk. So the force from the inner disk is stronger than the force from the outer disk. The same for the outer planet. Of course, the force from the outer disk is of course stronger than the force from the inner disk, but the force is also proportional to the mass of the planet. And since the inner planet is much more massive than the outer planet, both of them can move outwards.
Yeah, I'm going to have to think about it. Yeah, I think I will. I think I will come to understand it. And it's the resonancing which locks the two planets together and stops them acting separately.
Exactly.
But it's the same sort of force that actually causes the inward motion in the first place. I think you said.
Yes. So essentially so you have always this interaction of inner disk to planet to outer disk. But now in the idea, when you have two planets, you have the force of the inner disk onto the inner planet is much stronger than the force of the outer disk to the inner planet. That gives you a net force that is directing you outwards.
Yeah, I will get to understand that. When you've just got a single planet, though, there's a drag tending to drag it forward and therefore move it outwards, and there's another tending to drag it back and move inwards. I don't quite see why they don't balance, I think.
Yeah. So the difference in the balance is related to the mass of the disk, right? So the inner disk is less massive than the outer disk, right? Because most of the mass, so they have an different balance also in the masses of the.
The mass of the outer disk is bigger than.
Yes.
I understand. Thank you.
Back to Tony Morris.
on the simulation that you showed of planet formation, it looked in there that there was quite substantial planets formed within, say, 100 million years. It surprised me that those timescales seem much shorter than the first biological evolution of atmospheres. Is that, am I thinking about that the right way?
Well, I mean, so essentially the formation phase of the solar system would last, you know, 300 million years, something like this. But then the development of the atmospheres and so on takes much longer time, right? So if you look back, for example, at the Earth's atmosphere, now let's say like 1 billion years after formation, so 3.5 billion years ago, it's completely different compared to what we have now. So there's a lot of evolution going on into the evolution of the atmosphere in itself. So there's a different processes. Let's put it like this.
Okay, so would it be possible for a disk of low density to have a really, really slow evolution phase for the planets? And what
Yes.
does that look like?
So in a low density disk, the formation of the planets would take longer, or it might just stop, because the issue is that the disks don't live forever. So the disks normally live just a few million years, because then the density becomes so low that the leftover material of the gas and the dust is actually blown away by so-called photoevaporative winds. You can essentially think about something similar to radiation pressure from the sun that will accelerate the atom, the molecules into in the disk to velocities that allows them to escape the region around the sun. So the disks only live for a few million years. So if your disk is not very massive to begin with, it will be very, very difficult to form planets.
Okay, thank you.
Bert, I think I'm going to have the last question. And how does your model deal with planets around multiple stars?
Excellent question. So I actually personally never studied this. So there's of course we know that planets exist around binary stars. But things become much more complicated the moment you move to binary stars, because you suddenly have two gigantic masses that orbit also around each other and influence, for example, the structure of the protoplanetary disk and the gravitational interaction between the planets. So there's just a few studies that actually look into this, but the majority of planets that we have detected so far are actually around a single stars. So this is not let's say a super active field of research, even though we know that essentially half the stellar population is actually in binaries.
Okay, I'll watch that space then.
Yeah.
Ladies and gentlemen, can you join with me in giving Bert Bitsch a huge thanks for International Society? Thank you for an excellent talk.
Thank you.